right, so I just changed this one. It says this should read, is the test two-tailed? Then we double the p-value to compare it. So what I think they meant to have here was this one be a two-tailed, because remember in the last slide we only double the p-value when we have a two-tailed test. So I'm not quite sure why they said is the test statistic to the right or the left. I think they meant is the test statistic to the right and the left of the center. So basically, is there an area to the right and the left? Is it a two-tailed test? Because they already did left and they did right, and so this one is the only one that's left, which is two-tailed. So I'm not quite sure. That's just an odd little thing. I don't think it's a very good illustration of what's truly going on here. So then, let's say, how do we make that decision? Make a decision to either reject H sub O or fail to reject H sub O. We never say we accept H sub O. We just either reject it or we fail to reject it. The decision criteria for the p-value method, if the p-value is less than or equal to the alpha, then we reject the H sub O. If the p is low, the null must go. If the p-value is greater than alpha, we fail to reject the H sub O. So the decision criteria for the critical value method, if the test statistic is in the critical region, reject H sub O. If the test statistic is not in the critical region, then we fail to reject the H sub O. And it's as simple as that. So those are our two criteria that we're going to see some examples about shortly. And then that one is here the type of terminology that we're going to use, which is the 8th step. How do we word these things? So here we have the claim is H sub O, the claim is H sub A. If we reject H sub O when the claim is H sub O, we say there's enough evidence to reject the claim. If we reject H sub O when the claim is H sub A, we say there's enough evidence to support the claim. Okay, if we fail to reject H sub O when the claim is H sub O, then there is not enough evidence to reject the claim. If we fail to reject H sub O when the claim is H sub A, there is not enough evidence to support the claim, because the claim is the H sub O was not rejected and the claim is the H sub A. So those are the kind of cheats for how to word things. And then this one was from your text. This one here was from another textbook. And these are the ones, same thing, that are from your book. And they're pretty much the same thing. All right, so restate the decision using simple and non-technical terms. We never say accept. We always say fail to reject. Okay, we should say we fail to reject the null hypothesis instead of saying that we accept the null hypothesis. The phrase fail to reject says more correctly that the available evidence isn't strong enough to warrant a rejection. Okay, and then they're put in a little warning here about just multiple negatives in your wording. Try to make your wording clear, is what they're trying to tell you there. And then here is an example. You perform a hypothesis test for following a claim. How should you interpret your decision if you reject the H sub O? If you fail to reject the H sub O? So H sub O is the claim. A school publicizes that the proportion of its students who are involved in at least one extracurricular is 61%. So remember, the equal to position is the H sub O. So the claim is the H sub O. The H sub A is going to be the not equal to. So this one is a two-tailed test, okay? And since we're rejecting the H sub O, we are also rejecting the claim, okay? So you would say if you reject H sub O, then you should conclude that there is enough evidence to reject the school's claim that the proportion of students who are involved in at least one extracurricular activity is 61%. If you fail to reject the H sub O, then you should conclude there is not enough evidence to reject the school's claim that the proportion of students who are involved in at least one extracurricular activity is 61%. Okay, so the claim here is represented by the H sub O. All right, so then let's look at a second example here. This is the car dealership example. A car dealership announces that the mean time for an oil change is less than 15 minutes. So our H sub A is our claim. The H sub A is the less than. It does not involve an equal sign. So our H sub O is greater than or equal to. If we reject the H sub O, then our claim is seeming to be good. If we reject the H sub O, then you would conclude there is enough evidence to support the dealership's claim that the mean time for an oil change is less than 15 minutes. If we fail to reject, then you would conclude there is not enough evidence to support the dealership's claim. Okay, so the H sub A and the H sub O here, the H sub A was the claim. So here is another example that came from your book. Actually, this was not from your book. This was from yet another textbook that I scavenged some more examples from. This is also talking about how to interpret the conclusion. You can go through those confidence intervals. So here they're going back to the confidence interval method, which basically for proportions, they're going to say don't use the confidence interval method. For means, you should get the same result. But generally, this is not a focus of what we're trying to teach you here. So I wouldn't really worry too much about the whole confidence interval thing. It's in your textbook, but we're not focusing on that right now. That was chapter 7. We're focusing on chapter 8. But if I asked you to find the confidence interval for a situation, and then I ask you to do a hypothesis test and compare the results, you should be able to do that. Okay, so I do want you to think about the fact that it makes sense that a confidence interval is an estimate of the population parameter. It's going to contain the values that are likely for that parameter. If our tested value is not in the normal parameters here, then you would say, this doesn't look great. This looks kind of fishy. All right, so now let's talk about types of errors here for a minute. So when we're talking about types of errors,
what kind of book are you reading?
So let's continue with types of errors. No matter which hypothesis represents the claim, always begin the hypothesis test assuming that the equality condition of the null hypothesis is true. So we start out assuming that H sub 0 is true. At the end of the test, one of two decisions will be made. Reject the null hypothesis or fail to reject the null hypothesis. Because your decision is based on a sample, there's the possibility of making the wrong decision. Never say we accept. Okay, so here are the types of errors that occur. Suppose H sub O is true, and you do not reject H sub O. That is the correct decision. But what if H sub O is true and you actually reject it? That is called a type 1 error. A type 1 error occurs if the null hypothesis is rejected when it is true. Okay, suppose H sub 0 is false. That's its true situation, that it is false. We do not reject it. That means we made a type 2 error. We should have rejected it, but we did not reject it. That is a type 2 error. We did reject it, then we make the correct decision. So a type 2 error here occurs if the null hypothesis is not rejected when it is false. So we call alpha is the probability of a type 1 error, the probability of rejecting H sub O when H sub O is true, and beta is the probability of a type 2 error, the probability of failing to reject H sub O when it is false. All right, so this is an example that I got off of YouTube from a guy named Scott Crawford, and he had a very cool little website on statistics, and I got this one from him. I pirated his example, but I want to give him due credit. Scott Crawford, here you go. Guy meets girl at a social event. H sub 0, the guy is a creeper. So guy equals creeper. H sub A, the guy is your one true love. What would a type 1 error be? Okay, H sub O really is true. The guy is a major creeper and you reject that he is a creeper and he becomes your Prince Charming. How creepy is that? Okay, what would be a type 2 error? All right, the null is false. The guy is your one true love, but you think he's a creeper and you send him packing. So sad, true love thwarted. So I thought that was just a cute example of a type 1 and a type 2 error. So here we have another type 1 and type 2 error example here. Let's see if I can readjust this a little bit. All right, so the USDA limit for salmonella contamination for chicken is 20%. The meat inspector reports that the chicken produced by a company exceeds the USDA limit. You perform a hypothesis test to determine whether the meat inspector's claim is true. When will a type 1 or type 2 error occur? Which is more serious? Okay, so here we always put the equal sign on the H sub 0. So let P represent the proportion of chicken that is contaminated. So H sub 0 is P is less than or equal to 0.2, which means the chicken is okay. H sub A is P is greater than 0.2, so that's not good. And so remember, the meat inspector is saying that it is greater than 0.2. That's the claim. So if the H sub O is correct, then the chicken meets the USDA limits. If the H sub O is incorrect, okay, chicken exceeds. So basically that should say H sub A right there. That is a typo. That's H sub A. P is greater than 0.2. So then we have got this sliding scale. We don't know where it goes. This is our P, and we're not sure. But we do the test, okay, what is a type 1 error? A type 1 error is rejecting H sub O when it is true. So here, H sub O is we've got good chicken, but we reject that we have good chicken. Okay, the actual proportion of contaminated chicken is less than or equal to 0.2, but you decide to reject H sub O. With the type 1 error, you might create a health scare and hurt the sales of chicken producers who are actually meeting the USDA limits. A type 2 error is failing to reject H sub O when it is false. The actual proportion of contaminated chicken is greater than 0.2, but you do not reject H sub O. With the type 2 error, you could be allowing chicken that exceeds the USDA contamination limit to be sold to consumers. A type 2 error could result in sickness or even in death. Okay, so this is the game that we play in statistics, determining which error is more serious. Okay, describing a type 1 and type 2 error. Consider the claim the medical procedure designed to increase the likelihood of a baby girl is effective, so that the probability of baby girl is greater than 0.5. Given the following null and alternative hypotheses, write statements describing a type 1 error and a type 2 error. So H sub 0, P equals 0.5. Okay, so that's saying that it's not effective right there. H sub A, P is greater than 0.5, the original claim that will be addressed in the final conclusion. So a type 1 error is the mistake of rejecting a true null hypothesis. So the following is a type 1 error. In reality, P equals 0.5, but sample evidence leads us to conclude that P is greater than 0.5. In this case, a type 1 error is to conclude that the medical procedure is effective when in reality it had no effect. Okay, so not horrible, but still you're misinformed. A type 1 error would be thinking that there was some change due to the medication or procedure, but indeed it had no effect at all. And then a type 2 error in this case is the mistake of failing to reject the null hypothesis when it is false. So the following is a type 2 error. In reality, P is greater than 0.5, but we fail to support that conclusion. In this case, a type 2 error is to conclude that the medical procedure has no effect, when in reality, it's effective in increasing the likelihood of a baby girl. Okay, so again, this one is determining the type of error. A television executive believes that at least 99% of households in the United States have at least one television. An intern in the executive's company is given the task of using a hypothesis test to determine whether the percentage is actually less than 99%. The hypothesis test is completed, and based on the sample collected, the intern decides to fail to reject the null hypothesis. If in reality 96.7% of households own a television set, was an error made? If so, what type? Okay, so the executive believed that at least 99%, when in actuality it was 96.7%. Okay, so let's begin by writing the null hypothesis and the alternative hypothesis by asking, what is the intern gathering data for? Because the hypothesis test is being used to determine if the percentage is less than 99%, the research hypothesis H sub A is P is less than 0.99. The logical opposite is P is greater than 0.99, and this is the null hypothesis, greater than or equal to. So the two hypotheses are written as follows. The hypothesis test fails to reject the null hypothesis. However, since the reality is that P is 0.967 and thus the null hypothesis is false, the intern failed to reject a false null hypothesis. This is a type 2 error. So you have to know which one is your H sub O and which one is your H sub A. And then this one is another example. I'll let you do that one by yourself. And another example, I'll let you do that one by yourself. I always give you plenty of examples. So this one is actually the one that goes with your textbook, right? And this one is going all the way through, pointing out each one of these points with the example that's in your textbook. 1,009 consumers were asked if they were comfortable with having drones deliver their purchases, and 54%, which if you take 54% of 1,009, you get 547 of them responded with no. Using P to denote the proportion of consumers not comfortable with drone deliveries, the majority claim is equivalent to the claim that the proportion is greater than half, or P is greater than 0.5. The expression P is greater than 0.5 is the symbolic form of the original claim. So here we've got number 1 and number 2 already stated here. Okay, so now we've got to figure out how significant we want this to be. So the big picture is we have the claim that the population proportion P is such that P is greater than 0.5. Among 1,009 consumers, how many do we need to get a significantly high number who are not comfortable with drone delivery? The result of 506, which is 50.1, is just barely more than half. So that does not seem to be significantly high. A result of 1,006 is clearly significantly high. But what about the result of 541 that was actually obtained in the Bitney Bowles survey? Is 545 significantly high? The method of hypothesis testing allows us to answer that key question. Okay, so here we're going to talk about using technology. It is easy to obtain hypothesis testing results using technology. And we're going to see this more as we go into each one of the different types. Remember, this first section is a big overview of hypothesis testing, and we're going to get more nitty-gritty as we go along. So the first one says it is easy to obtain hypothesis testing results using technology. The accompanying screen that I'm about to turn to displays results from 4 different technologies, so we can use computers or calculators to do all of the heavy computational lifting. So we're going to examine the 4 screens and we're going to see some common elements. They all display a test statistic of z is 2.55, and they all include a p-value of 0.005. So we're going to see those in a minute. And it says focus on understanding how the hypothesis testing procedure works and learn the associated terminology. Only then will the results from technology make sense. So now you can see the 4 screens that we were talking about. Here's a stat disk, a mini tab, TI-83, TI-84, and a stat crunch, okay? The only ones that we've used was stat disk and TI-83, TI-84. We're going to be doing this with the TI-83, TI-84 because that's the one you have access to during the test. But what they're trying to get you to see now, like this is just an overview, is that the technology exists for you to be able to just stick a couple things in your calculator and you get out your test statistic and your p-value there. So we'll learn more about that as we go along. So then the significance is what test of significance is what hypothesis tests are also called. Now we use probabilities to determine the sample results were significantly low or significantly high back in section 4.1. This chapter formalizes those concepts in a unified procedure. So again, this is an overview of what we're talking about. And then they're stepping you through step 1, step 2 with the drone delivery here. Step 3 is coming up with a H of O and an H of A. Then we're going to talk about the test statistic that we found from the technology, or the p-value that was found by the technology. And as we move on into 8.2 and 8.3, we're going to see which technology we use with each one of the different situations that we're going to have. But this gives us our test statistic and our p-value. And then when we go to that test statistic here, that got cut off right there, but the test statistic that goes with the 95% confidence level, which we're going to use because that's the most normal one that we have, is 1.645, which you can get from your chart. And the claim, so we had our H sub O and H sub A, so this is just a picture of what happens with a hypothesis test. Okay, so then we find our test statistic, 2.54, using the formula. This is if we didn't have the technology, we would have to do it this way. And notice that the 2.55 came from the technology and the 2.54 came from doing this. But if we turned, instead of using the estimate here, we used the exact proportions, we would get the same thing. And that is the end of 8.1. So 8.1 is strictly an overview, and we're going to start into 8.2, which is talking about hypothesis testing for proportions.